All right, so the other potential energy that we'll deal with this semester is the elastic potential energy. The spring force is the second conservative force that we have. So if we take a mass and attach it to the end of the spring, so here's a spring where we've got one end attached to the wall and a mass attached to the other end. We'll treat this as a frictionless surface that it's oscillating back and that it's moving around on. And you notice that what I can do is I can pull the mass out by pulling it to the right, and I can push the mass in by pushing it to the left, and in both cases I'm moving it away from the equilibrium point. And so the question becomes, in which direction does the elastic force pull on the mass whenever I do that? And in either case, the elastic force is always trying to pull the mass back towards equilibrium. So here you can see that the spring force, when I pull the mass out to the right, the spring force is trying to pull the mass back to the left, back towards equilibrium. When I pull the mass out to the, or when I push the mass over to the left, the spring force is trying to push the mass to the right, again, back towards equilibrium. So I know that the change in the elastic potential energy is going to be equal to negative the work done by the spring. And so conceptually what that means is, since the spring force is always trying to get the mass back towards equilibrium, is that when I move the mass away from equilibrium, then I have to increase the elastic potential energy. So that's moving the mass in the direction that's the opposite of the direction the spring force is trying to pull on it. So that obviously has to increase the elastic potential energy. On the other hand, if I let the mass move towards equilibrium, so let's say pull it out over here to the right and then let it go, well, obviously the spring is going to pull it back towards equilibrium. So the spring is doing positive work in that case, and that's going to decrease the elastic potential energy. So conceptually, it's pretty easy to figure out whether I'm increasing or decreasing the elastic potential energy based on whether I'm moving towards or away from equilibrium. When we calculated the work, we said, well, the work done by a spring is equal to negative 1/2, K here again is our spring constant, times the final displacement from equilibrium squared minus the initial displacement from equilibrium squared. So if you start with the mass some distance away from equilibrium and you pull it so that it's a new second distance away from equilibrium, I can plug those two displacements in here and here, square them, multiply by K, multiply by negative 1/2. That's going to give me the work done by the spring. Again, the spring does positive work when the mass moves towards equilibrium, and it does negative work as the mass moves away. Well, just using my calculation, or my relation for how the change in potential energy is related to the work done by a conservative force, I know that the change in the elastic potential energy is equal to negative the work done by the spring. So this negative sign here is going to combine with the negative sign that was in my work equation from the previous slide. Those two are just going to leave this being positive. So I've got exactly the same expression, it's just in this case there's no negative sign sitting out front. So the change in the elastic potential energy is given by 1/2 K, again my spring constant, times final displacement from equilibrium squared minus initial displacement from equilibrium squared. If I move away from equilibrium, well, that means my final value is larger than my initial value in terms of these two displacements. So I've got something bigger squared minus something smaller squared. This is going to be positive, which means that moving away from equilibrium gives me an increase in the elastic potential energy. And again, that checks with conceptually what we said had to happen on the very first slide. If, on the other hand, I move towards equilibrium so that my final value here is less than my initial value in terms of these two displacement values, then this, whatever's inside the parentheses here, will end up being negative, right? Something small squared minus something big squared is going to end up being negatively valued. K is always a positively valued constant, so that means that my change in the elastic potential energy would be negative, which again tells me that I have a decrease in the elastic potential energy when my mass moves towards equilibrium. So again, that checks out just like we expected it to. If you want to talk about the elastic potential energy, again, what that really means is the elastic potential energy relative to the point where the elastic potential energy equals 0. We never say all that, but we've got to be very clear that that's what we always mean. So we have to have a 0 point. And the easiest thing to do is simply to set up our 0 point to be at equilibrium. So wherever the spring wants to come to a rest, that's going to be where we set the 0 point for elastic potential energy. So then we can calculate the elastic potential energy for the mass at any point relative to the 0 point at equilibrium by just doing 1/2 kx squared. So part of what this means is that elastic potential energy, when we calculate the elastic potential energy, it'll never be negative when we set it up this way. So we'll just always multiply 1/2 times our positive valued spring constant times, again, some distance that's getting squared, so we know that that's going to be positively valued. So we'll never have a negative u sub s when we're using our 0 point at equilibrium. All we're going to care about then is just the spring constant and then the distance that the spring is stretched or compressed to calculate the elastic potential energy.